Unified field theories, pursuing a single mathematical framework. Unified field theories, pursuing a single mathematical framework. Introduction. The quest to understand the fundamental forces of nature has fascinated scientists for centuries. Throughout the history of physics, various theories have been developed to explain these forces, from classical mechanics to quantum theory. Yet, the holy grail of physics remains the discovery of a single mathematical framework that unifies all these forces, known as a unified field theory. What is a unified field theory? Currently, these forces are described by separate theories, general relativity and quantum field theory, which are mathematically incompatible. A unified field theory seeks to bridge this gap, providing a deeper understanding of the universe. A historical perspective. The quest for a unified field theory dates back to the great minds of the 20th century. Albert Einstein, the father of modern physics, spent the later years of his life attempting to unify gravity with electromagnetism. His theory of general relativity provided a geometric description of gravity, but it failed to incorporate the other fundamental forces. In the following decades, numerous physicists, including Werner Heisenberg and Wolfgang Pauli, attempted to develop further unified theories. However, progress was hindered by the lack of experimental evidence and the technical challenges involved in reconciling the fundamental forces at different energy scales. String theory in the pursuit of unification. In the 1970s, string theory emerged as a promising candidate for a unified field theory. It postulates that fundamental particles are not point-like, but rather tiny vibrating strings. String theory naturally incorporates gravity and can potentially unify all forces. However, it requires a mathematical framework that extends beyond the traditional four-dimensional spacetime of general relativity. String theory exists in several versions, including superstring theory and M-theory. These theories suggest the existence of additional dimensions, beyond the familiar four dimensions of space and time. While this may seem counterintuitive, these extra dimensions are assumed to be curled up or compactified to microscopic scales, making them undetectable in our everyday experience. The challenges and criticisms. Despite its promise, string theory faces numerous challenges and criticisms. One major criticism is the lack of experimental evidence, as it currently cannot be directly tested through experiments. This has led some physicists to question its scientific validity, arguing that it may be more of a mathematical framework rather than an actual physical theory. Additionally, string theory's landscape problem presents a formidable challenge. The theory predicts a vast number of vacuum states or string landscapes, each potentially representing a different set of physical laws. Determining the precise vacuum state that corresponds to our universe remains an unsolved puzzle. Furthermore, the complexities of string theory require novel mathematical techniques and concepts, such as advanced geometry and non-perturbative methods. This presents a significant obstacle to its development and widespread acceptance. Alternative approaches. While string theory dominates the pursuit of a unified field theory, alternative approaches have also emerged. Some physicists explore the possibility of an underlying quantum theory of gravity, such as loop quantum gravity or causal dynamical triangulation. These approaches differ from string theory and attempt to unify the forces using different mathematical frameworks, such as discrete spacetime structures. Another competing approach is known as quantum field theory on curved spacetime, pursued by researchers like Stephen Hawking and Roger Penrose. This approach attempts to incorporate gravity into the framework of quantum field theory, without relying on string-like objects. However, it faces challenges in resolving the incompatibility between general relativity and quantum mechanics. The importance of a unified field theory. The discovery of a unified field theory would revolutionize our understanding of the universe and profoundly impact various scientific fields. From cosmology to particle physics, a TOE would provide a deeper insight into the fundamental nature of reality. Practical applications could also arise from a unified field theory. Moreover, a unified field theory could shed light on the earliest moments of the universe, explaining the phenomena that occurred during the Big Bang. It would allow us to gain a more comprehensive picture of our cosmic origins. The search for a unified field theory, or theory of everything, TOE, has captivated scientists for centuries. By aiming to explain all the fundamental forces of nature within a single mathematical framework, a unified field theory holds the promise of deepening our understanding of the universe. Throughout the history of physics, various theories have been developed to describe the fundamental forces, such as gravity, electromagnetism, and the strong and weak nuclear forces. However, these theories, such as general relativity and quantum field theory, are mathematically incompatible. The challenge then is to bridge this gap and find a unified explanation for all these forces. The quest for a unified field theory can be traced back to the 20th century, where great minds like Albert Einstein, Werner Heisenberg, and Wolfgang Pauli attempted to develop unified theories. However, progress was hampered by the lack of experimental evidence and the technical difficulties involved in reconciling the forces at different energy scales. In the 1970s, string theory emerged as a promising contender for a unified field theory. It proposes that fundamental particles are not point-like but instead tiny vibrating strings. String theory naturally incorporates gravity and has the potential to unite all forces. However, it requires a mathematical framework that extends beyond the four-dimensional spacetime of general relativity. These extra dimensions are assumed to be compactified to microscopic scales and are not observable in our everyday experiences. Despite its promise, string theory faces challenges and criticisms. One major criticism is the lack of experimental evidence, as it cannot be directly tested at present. Some physicists argue that it may be more of a mathematical framework rather than an actual physical theory.